So we're going to use combinations to work with binomial theorem, which is like Pascal's triangle. So we're going to try to relate some ideas here. Pascal's triangle is what we have here. Essentially, we always have a 1 on the outside of the triangle, and then you continuously add the middle terms to figure out what the next ones are. So this can help with binomial distribution if we have two terms, and you kind of think of the idea of FOIL to the power of 0. This would tell you what the coefficient would be on the very first one. If it was just to the power of 1, well, the coefficients in front of this would be 1 and 1. If we go to the power of 2, okay, assuming that these coefficients are 1 here, you would end up with 3 terms, 1, 2, 3, and the coefficients would be 1, 2, 1. If you're putting the binomial to the power of 3, you're going to have 4 terms, okay, and the coefficients are going to be 1, 3, 3, 1. So it kind of tells you the coefficients in front of all of the terms, and then from there you just kind of work down your numbers. For instance, if this was, say we're actually going to do the third one. Let's say we actually want to do a plus b to the power of 3. The coefficient would be 1a cubed, okay? And then technically it's b to the 0. Think of it like that, but we don't write b to the 0 in because it's just the number 1. The next number would be 3a2b1. The next one would be 3a1b2, and I can squeeze the last one in. The last one would be 1 a0b3, and again the b0 and the a0 you don't need to include because they're just the number 1. Okay, so that's how these relate. They are the coefficients in front of our binomial distribution, and really you just start with the first one, and because there's going to be because it's to the power of 3, we start with that number 3 and count down for the exponents 2, 1, 0. And then for the second term, you do the opposite. You start with 3 on the right and count down 2, 1, 0 to the left. So you can kind of build them really, really quickly if you understand it. Now, what becomes difficult is if they ask you to like go to something like the 12th term, right? To build Pascal's triangle to the 12th term, well, since 0, okay, is the first row, the power of 12 would actually mean the 13th row. Okay, which means there's going to be 13 terms involved. So this number, whatever the power is, always know that plus 1 will tell you the number of terms that are going to actually be in it, right? To the power of 3, give us 1, 2, 3, 4 terms. Okay, so that's like a quick trick to figure out how many terms there are. Instead of working this triangle, you can use something on your calculator called combinations. Okay, and the combinations kind of relate to our powers. A combination. There's a formula for it, but since we're just going to be using it, we don't really want to understand it too much. It's usually used a lot more in probability, but the idea here is our first row is 0 combination 0. Okay, our second row is the number 1, and then we would start with the first combination of 0 and then the next number 1. So we count across the row. So we can use these numbers to figure it out. So the third row, we know there's going to be 4. Okay, we would say 3 combination 0. That will tell us the first term. And if you put that in a calculator, that's going to give you the number 1. If you put 3 combination 1, that's the next term. That would give you the number 3. 3 combination 2, that would give you the number 3. And 3 combination 3 gives you the number 1 again. So let's look down here. We want to build to the power of 5. I don't feel like going to the 6th row of Pascal's triangle, though it's really not that far. We know to the power of 5 means there's going to be 6 terms, so we can already kind of lay that out. We know we're going to have 1, 2, 3, 4, 5, 6 different terms because it's to the power of 5. And I want to know what the coefficients are going to be in front of everything. We can actually build all the exponents first. Like we said, remember, if our first term or value is x, the very first term would be x to the power of 5. Then x to the power of 4, then x to the power of 3, x to the power of 2, x to the power of 1, and then x to the power of 0. Okay. The second term, you would also multiply. It's going to be negative 3, so we'd have negative 3. Actually, I should start over here. Negative 3 to the power of 5, negative 3 to the power of 4, negative 3 to the power of 3, negative 3 to the power of 2, negative 3 to the power of 1, and negative 3 to the power of 0. Now, obviously, those 2 zeros we can leave out, but they just kind of help us organize everything we're doing. The last thing we need to do is figure out what the coefficients are going to be, and that's where Pascal's triangle comes in handy. Okay, so this helps us build all of the, and usually sometimes there's like two variables here, so this would be like a letter y or something. But this helps us build all the terms, the coefficients. Well, because we know we're in the fifth row, we can deduce that we're going to have the very first one is going to be 5 combination 0. So that will give us our first coefficient. The next coefficient will be 5 combination 1, 5 combination 2, 5 combination 3, 5 combination 4, and then 5 combination 5. Now, it's pretty obvious because we know Pascal's triangle that the first one's going to be the number 1 and the last one's going to be the number 1. We know that because that's how the triangle always has the outside ones. But these middle terms we're not quite sure because we don't know what we're adding. So we can put these into a calculator that does combinations. So I've kind of already set one up. Okay, and the first term in the combination, I'm going to say 5. So we're going to look for 5, 1. It tells us the number is positive 5. Okay, so the next term we're going to say plus 5. For the next one, same idea. We'll just kind of go through this. So 5 to the 2 gives us 10. Okay, so we say plus 10. And since we already know that this is symmetrical stuff, okay, when I had the 1 over here, I know that this would also be plus 5. So if we were to actually put that in, 5 combination 4, you get 5. And then this will also be 10. So you can almost only do half of them, and you know it will kind of be symmetrical. This isn't done, though. Even though this looks really, really confusing, the reason it's not done is because this actually gives us a number, this negative 3. It'll give us a number every time, so we actually have to equate this power. When it's to a variable, there's nothing we can do. We just leave it to that power. But because this is a number, we're going to have to multiply it by that coefficient, and that'll give us a new coefficient. So negative 3 to the power of 0 is 1, and 1 times 1 is 1. So we can really just write the very first term, or write in black as our final answer, as x to the power of 5. Okay. The next one, this should be to the power of 1. Negative 3 to the power of 1 is negative 3 times 5 is going to give us negative 15. So we have negative 15 x to the power of 4. Okay. Negative 3 to the power of 2, that's going to give us positive 9. Positive 9 times 10 is going to be positive 90 x to the power of 3. Okay. Negative 3 to the power of 3 should be negative 27 times 10 will be negative 270. And then I'm starting to get out of my round. I think that's 81. 81 times 5 will be 405. We're going to check that one after. And sorry, this should be x to the power of 2, x to the power of 1. And negative 3 to the power of 5, I don't know what that is. I know it's going to be negative. 3 power of 5, so it would be negative 243. Okay. So I know I went through this part really quickly, but we kept the variable the same throughout all of them. Okay. And we just did a little extra multiplication with those coefficients. If this had been just a power, a variable, like the letter y, we wouldn't have had to change the coefficient. These would have been our final answer. But because this was actually a constant term, we had to equate it and then multiply it by whatever the coefficients we found with those combinations are. Okay.